Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the hidden magnetic conversation between our sun and Earth, a dialogue that has whispered across space for billions of years, shaping the very conditions that allow life to flourish. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The sun breathes, not with lungs, not with the rise and fall of chest and ribs, but with something far more ancient and patient. From its corona, that ghostly atmosphere visible only during eclipses, streams of charged particles flow outward at speeds that would cross continents in heartbeats. This solar wind carries with it the sun's magnetic signature, invisible threads of force that stretch between planets like the finest silk woven from starlight and time. For 4.6 billion years, this wind has blown without pause. It has never known a moment's rest, never experienced the quiet of a still morning or the hush of evening calm. Scientists measure its velocity at roughly 400 kilometers per second on average, though during solar storms it can surge to twice that speed, racing through the vacuum at 800 kilometers per second. To put this in perspective, such particles could travel from New York to Los Angeles in roughly 5 seconds. Only took our star a few billion years to settle into this rhythm. The particles themselves appear deceptively simple, mostly protons and electrons, the basic building blocks of hydrogen torn apart by the sun's immense heat. Each cubic centimeter of space near Earth contains about 5 of these particles, a density so sparse it makes the best laboratory vacuum seem crowded by comparison. Yet, in their journey across the 150 million kilometers of space that separate Sun from Earth, they carry something profound information written in magnetic fields, a kind of cosmic script that tells the story of solar weather, of magnetic loops erupting from the sun's surface like slow-motion fountains of plasma, of the 11-year cycle that governs our star's mysterious moods. The solar wind emerges from coronal holes regions where the sun's magnetic field lines stretch out into space rather than looping back to the surface. Here, in these magnetic valleys, particles find their escape routes, following invisible highways that have existed since the sun first ignited its nuclear furnace. The process resembles water finding the path of least resistance down a mountainside, except the mountain is made of magnetic force, and the water consists of particles moving at nearly 1% the speed of light. Scientists still puzzle over exactly how the solar wind accelerates to such tremendous speeds. The corona, paradoxically, burns at temperatures exceeding 1 million degrees Celsius, roughly 300 times hotter than the sun's visible surface, a mystery that has persisted for decades despite our most sophisticated observations. The visible surface, the photosphere, maintains a relatively cool 5,500 degrees Celsius. Yet somehow, the corona above it blazes with incomprehensible heat. Somehow, magnetic waves and reconnection events conspire to fling these particles into the void, creating what astronomers call a supersonic flow that defies simple explanation. The sun's magnetic field itself wraps around our solar system in a vast spiral pattern, like the grooves on an enormous phonograph record rotating once every 27 days. This creates what scientists call the Parker spiral, named after physicist Eugene Parker, who first described how the sun's rotation stretches its magnetic field into elegant curves that sweep past each planet in turn. Only took humanity until 1958 to figure out why compass needles sometimes dance during auroras. Earth waits in this cosmic stream like a smooth stone in an eternal river, but it is far from defenseless. The planet possesses its own magnetic personality, a shield generated 2,900 kilometers beneath our feet in the liquid iron of its outer core. Here, in temperatures that match the sun's surface, iron flows in vast currents driven by the planet's rotation and the heat escaping from its solid inner core. These motions generate electric currents, and electric currents create magnetic fields, a planetary dynamo that has operated continuously for at least 3.4 billion years. This terrestrial magnetic field extends far into space, creating a bubble-like region called the magnetosphere that encompasses our planet like an invisible cocoon. On the day side, where it faces the incoming solar wind, this magnetic boundary compresses to roughly 60,000 kilometers from Earth's surface, about 10 times the planet's radius. On the night side, it stretches into a long tail that extends beyond the moon's orbit, creating a magnetic wake like that behind a ship moving through water, except this wake extends for millions of kilometers through the vacuum of space. When solar wind meets terrestrial magnetosphere, the result is neither violent collision nor simple deflection, but something more elegant, a conversation between magnetic fields that speak the same fundamental language. The boundary where they meet, called the magnetopause, fluctuates like a living membrane, breathing in and out with the rhythm of solar wind pressure. During quiet periods, it expands outward. When solar storms arrive, it contracts inward, sometimes compressing to half its usual distance from Earth. This dialogue unfolds in slow time, measured not in seconds or minutes, but in the patient accumulation of magnetic pressure, in the gradual warping of field lines that curve and twist like invisible rivers of force, in the quiet dance of charged particles finding their way through corridors that exist only in the mathematics of electromagnetism. The process involves what physicists call magnetic reconnection moments, when magnetic field lines from the Sun and Earth touch, merge, and suddenly snap apart like rubber bands, releasing energy in brief, soundless explosions that illuminate the upper atmosphere. At the poles, where Earth's magnetic field lines funnel downward toward the surface, solar wind particles follow these invisible guides into the atmosphere, creating aurora sheets of light that ripple across the sky in colors determined by the gases they encounter. Oxygen glows green and red. Nitrogen burns blue and purple. These displays occur roughly 100 kilometers above the surface, in the thin air where the boundary between Earth and space becomes beautifully ambiguous. Only took evolution 4 billion years to produce observers capable of detecting this ancient exchange, to build instruments sensitive enough to measure magnetic fields weaker than those generated by refrigerator magnets, to recognize that the dancing lights in polar skies represent a conversation between our planet and our star that began long before the first cell divided, long before the first ocean formed, long before the solid ground beneath our feet had finished cooling from its molten birth. The solar wind carries with it the magnetic history of our sun, evidence of storms that raged across its surface when Earth was young, records of magnetic cycles that have pulsed with clockwork regularity for billions of years. In this sense, every particle that streams past our planet is a messenger from the sun's past, a carrier of information about nuclear fires that burned when the solar system was barely recognizable, when Jupiter and Saturn were still gathering the gas that would make them giants, when Earth was a molten ball, slowly learning how to breathe. Earth's invisible shield forms not in the atmosphere where clouds gather, not in the oceans where life will eventually stir, but deep within the planet's molten heart, where pressures exceed those found at the bottom of the deepest ocean trenches and temperatures rival the surface of the sun. Here, 2,900 kilometers beneath the solid ground where future forests will root and cities will rise, liquid iron flows in currents vast and patient, driven by forces that dwarf hurricanes and monsoons, creating the magnetic field that will protect all future life from the solar radiation streaming endlessly through space. The outer core, a shell of molten iron and nickel roughly 200 to 300 kilometers thick, surrounds Earth's solid inner core like a metallic ocean that has never known the touch of wind or the pull of tides. Yet this iron sea moves with its own profound rhythms, stirred by the planet's rotation, by temperature differences between the scorching inner core and the relatively cooler mantle above, by chemical gradients that develop as lighter elements separate from heavier ones in the eternal darkness of Earth's interior. These motions, invisible and silent, generate electric currents measured in millions of amperes flows of charge that would power entire civilizations if they could somehow be tapped. Electric currents create magnetic fields. This fundamental principle of physics operates whether the current flows through a copper wire in a laboratory or through molten iron in a planetary core. But the scale here defies human comprehension. Currents that circle the globe, magnetic field lines that stretch from pole to pole, a dynamo mechanism that converts the kinetic energy of flowing metal into the electromagnetic force that shields Earth from cosmic radiation, only took the planet about 500 million years after its formation to establish this protective system. The process begins with convection, the same phenomenon that drives weather patterns in the atmosphere, but here played out in liquid iron at temperatures exceeding 4,000 degrees Celsius. Hot iron rises from near the inner core boundary, carrying heat toward the core mantle boundary 200-300 kilometers above. As it rises, it cools slightly and eventually sinks back down, creating convection cells that persist for millions of years. The Coriolis force, generated by Earth's rotation, deflects these rising and sinking currents, organizing them into helical patterns that spiral around the planet's axis like enormous metallic tornadoes moving through molten space. These helical flows stretch and twist magnetic field lines, amplifying them through a process scientists call the dynamo effect. Imagine holding both ends of a rubber band and twisting one end. The band becomes tighter, storing more energy. The geodynamo works similarly, except instead of rubber bands, it manipulates invisible lines of magnetic force, and instead of human hands providing the twist, planetary rotation and convective motion combine to strengthen and maintain the magnetic field. The mathematics describing this process fills textbooks, yet the essential mechanism remains elegantly simple. Moving metal creates magnetism, but the geodynamo possesses subtleties that continue to puzzle researchers. Computer simulations attempting to model core dynamics require some of the world's most powerful supercomputers, running for months to simulate what happens in Earth's core over mere centuries. The equations governing magnetohydrodynamics, the behavior of electrically conducting fluids in magnetic fields, exhibit chaotic properties that make long-term prediction nearly impossible. Small changes in initial conditions can lead to dramatically different outcomes. A sensitivity that helps explain why Earth's magnetic field varies in strength and direction over geological timescales. The magnetic field that emerges from these deep processes resembles, to a first approximation, the field that would be generated by a giant bar magnet tilted about 11 degrees from Earth's rotational axis. But this simple description masks extraordinary complexity. Superimposed on the main dipole field are smaller scale features, magnetic anomalies that reflect the chaotic nature of core convection. Regions where the field strength varies by factors of 2 or 3, areas where field lines emerge from the Earth at unusual angles. Paleomagnetic studies investigations of ancient magnetic fields preserved in rocks reveal that Earth's magnetic field has varied dramatically throughout geological history. Sometimes it strengthens to twice its current intensity, sometimes it weakens to mere fractions of its present strength. During the weakest periods, the magnetic poles wander across the planet's surface like lost travelers, sometimes moving thousands of kilometers in relatively brief geological intervals. Only took geophysicists until the 1960s to realize that continents drift and magnetic poles dance to similar rhythms of deep time. The field's strength today measures roughly 25 to 65 microteslas at Earth's surface, about 100 times weaker than the magnetic field produced by a typical refrigerator magnet, yet strong enough to deflect the majority of charged particles streaming from the sun. This seemingly modest field strength belies the immense energies involved in its generation. The total energy stored in Earth's magnetic field could power human civilization for hundreds of thousands of years, if only we could access it. Instead, it flows freely into space, creating the magnetosphere that extends far beyond the atmosphere, a magnetic bubble that encompasses the entire planet and reaches past the moon's orbit. Scientists studying the geodynamo have identified several competing theories for exactly how Earth maintains its magnetic field. The prevailing model involves thermal convection driven by heat, escaping from the solid inner core as it slowly grows through crystallization of liquid iron. As iron atoms join the crystal lattice of the inner core, they release latent heat, creating temperature differences that drive convection in the outer core. This process also releases lighter elements that had been dissolved in the liquid iron, creating additional buoyancy forces that help sustain convective motion. Yet mysteries persist. Why did Mars lose its magnetic field while Earth retained it? Why does Venus, similar to Earth in size and composition, generate no detectable global magnetic field? How did Earth's magnetic field behave during the planet's earliest history? When the core was hotter and the inner core had not yet begun to crystallize, seismic studies suggest the solid inner core may have formed relatively recently in geological terms, perhaps within the last billion years, raising questions about how the geodynamo operated during Earth's first 3 billion years. The magnetic field lines themselves, invisible to direct observation, can be mapped using sensitive magnetometers carried by satellites orbiting hundreds of kilometers above Earth's surface. These field lines emerge from the southern hemisphere, curve through space in graceful arcs, and re-enter the Earth in the northern hemisphere, creating closed loops that guide charged particles along predictable paths. Near the equator, field lines stretch far into space. Near the poles, they dive steeply downward, creating the funnel-like geometry that will eventually channel aurora-producing particles into Earth's upper atmosphere. Deep in the outer core, where this magnetic architecture originates, iron continues its ancient circulation, indifferent to the life that will eventually flourish under its protection, unaware that its motion creates the invisible shield that makes complex chemistry possible on Earth's surface. The convection patterns that drive the geodynamo operate on timescales measured in thousands of years, while magnetic field reversals occur every few 100,000 years on average. Only took Earth's magnetic field 4 billion years to become essential for life, and life is still figuring out how to say thank you. The first magnetic storms arrive before Earth has learned to wear an atmosphere of oxygen, before the first cell has divided, before the planet's surface has cooled enough to hold liquid water for more than a few thousand years at a time. These storms are not weather in any sense that future meteorologists would recognize. No clouds gather, no winds blow, no rain falls. Instead, they represent the collision between two invisible forces, the strengthening solar wind carrying the sun's magnetic tantrums across space, and Earth's newly stabilized magnetosphere, that bubble of magnetic protection still learning its own geometry. When a coronal mass ejection erupts from the sun's surface, it hurls billions of tons of plasma into space at speeds exceeding normal solar wind velocities by factors of 2 or 3. These magnetic clouds, each one large enough to engulf several Earths, carry with them twisted bundles of magnetic field lines that originated in the sun's corona, frozen into the plasma like DNA strands carrying genetic information across interplanetary distances. The journey from Sun to Earth takes between 1 and 3 days, depending on the ejection's initial velocity and the density of the solar wind it encounters along the way. During the Hadean and early Archean eons, when Earth's magnetic field was perhaps half its current strength and still finding its equilibrium, these solar storms would compress the magnetosphere to unprecedented limits. The magnetopause, that flexible boundary where Earth's magnetic field meets the solar wind, would collapse inward to perhaps 30,000 kilometers from the planet's surface, less than half its quiet time distance. Imagine Earth's magnetic shield as a soap bubble being squeezed by invisible hands, deforming and flexing, but somehow maintaining its integrity against pressures that could strip away entire atmospheres. The compression triggers a cascade of electromagnetic processes that illuminate the upper atmosphere in colors no eye has yet evolved to perceive. Charged particles, accelerated by magnetic reconnection events at the magnetopause, follow field lines toward the polar regions like drops of water following grooves carved in stone. As they enter the thin atmosphere, roughly 100 kilometers above the surface, they collide with molecules of nitrogen, oxygen, and trace gases, transferring energy that causes these atmospheric constituents to glow with characteristic wavelengths of light. But the early Earth's atmosphere contains little free oxygen, perhaps 1 part in 10 million compared to today's 21%. Instead, the upper atmosphere consists primarily of nitrogen, carbon dioxide, water vapor, and trace amounts of methane and hydrogen. When solar wind particles strike these molecules, they create aurora displays dominated by the red light of excited nitrogen and the blue-green emissions of carbon dioxide, painting the sky in hues that would seem alien to future observers accustomed to the green and red aurora of an oxygen-rich world. These primordial aurora dance across skies that witness no sunset or sunrise in the modern sense, for the sun appears as a smaller, dimmer star than the one that will eventually power photosynthesis and warm the oceans where life will emerge. The young sun produces roughly 30% less energy than its mature counterpart, yet paradoxically generates more intense magnetic storms due to its higher rotation rate and more chaotic magnetic field structure. Solar storms that would be considered extraordinary in the modern era occur with routine frequency, sometimes lasting for weeks as successive coronal mass ejections follow one another across interplanetary space like waves in a cosmic ocean. The magnetic field lines themselves become visible during these intense storms, not through direct illumination, but through their effects on the aurora displays they guide. Curtains of light follow invisible magnetic highways from the magnetosphere's outer boundary to the polar atmosphere, creating patterns that reveal the three-dimensional structure of Earth's magnetic field. These aurora curtains can extend for thousands of kilometers across the sky, rippling and flowing as magnetic field lines stretch and snap back like rubber bands under the pressure of the solar wind. Scientists studying these ancient magnetic storms must rely on indirect evidence preserved in the oldest rocks on Earth. Magnetite crystals formed during the Archean eon retain memory of the magnetic field, strength, and direction when they crystallized, providing snapshots of conditions billions of years ago. These paleomagnetic records suggest that early magnetic storms were indeed more intense than modern ones, capable of reversing the local magnetic field direction for hours or days at a time as particularly powerful solar events overwhelmed Earth's magnetic defenses. The storms also generate electric currents in Earth's upper atmosphere and on the planet's surface, creating what geophysicists call geomagnetically induced currents. These currents flow through any conducting material they encounter, the oceans that are just beginning to form, mineral deposits near the surface, even the molten rock that still comprises much of the early crust. In the modern world, such currents can disrupt power grids and communication systems. In the Hadean Earth, they simply add another source of energy to the complex chemical processes already reshaping the planet's surface. Only took the solar system about 100 million years to settle into the rhythm of magnetic storms and recoveries that would persist for billions of years. The Sun's magnetic activity follows an 11-year cycle that may have been shorter and more intense during its youth, creating a drumbeat of electromagnetic disturbances that early Earth learned to absorb and deflect. Between major storms, the magnetosphere slowly recovers its shape, expanding outward as solar wind pressure decreases, healing the magnetic wounds inflicted by coronal mass ejections through processes that operate automatically, without conscious guidance or external intervention. During the recovery periods, Earth's magnetic field exhibits a phenomenon that scientists call flux ropes, twisted bundles of magnetic field lines that store energy like coiled springs. When the next solar storm arrives, these flux ropes can uncoil suddenly, releasing their stored energy and triggering additional aurora displays hours or days after the initial impact. The timing of these delayed responses depends on the complex geometry of magnetic reconnection, on the angle between Earth's magnetic field and the magnetic field carried by the solar wind, on variables that modern supercomputers struggle to predict with complete accuracy. The early magnetic storms also begin shaping Earth's upper atmosphere in ways that will prove crucial for the eventual development of life. High-energy particles from the Sun drive chemical reactions that would not occur under normal conditions, creating trace amounts of complex molecules that rain down onto the planet's surface. Some of these molecules may serve as precursors to organic chemistry, though the details of this process remain speculative. Only took organic chemistry about 1 billion years to figure out how to make copies of itself. The aurora themselves persist for hours or sometimes days during the most intense magnetic storms, creating a nearly continuous display that bathes the planet in ethereal light. This illumination reflects off the surfaces of the first permanent bodies of liquid water shallow seas that form as the planet finally cools enough to prevent water from immediately boiling away. In these primordial pools, the dancing lights of aurora create patterns that shift and flow like living things, foreshadowing the actual life that will eventually emerge from similar chemical processes occurring in similar environments, under the protection of the same magnetic field that makes these aurora possible. The dynamo's quiet revolution unfolds in the planet's metallic heart with a patience that spans geological epochs, establishing patterns that will persist for billions of years while continents drift, supercontinents assemble and fragment, and life experiments with increasingly complex forms in the oceans above. Deep within Earth's outer core, where liquid iron flows at temperatures that exceed 4,000 degrees Celsius. Convective currents organize themselves into a remarkably stable system, a planetary engine that converts the kinetic energy of flowing metal into the electromagnetic force that will shield all future evolution from cosmic radiation. The revolution is quiet in the sense that no sound can travel through the solid mantle that separates the core from Earth's surface. Yet the energies involved dwarf anything occurring in the atmosphere or oceans. Convection cells the size of continents rise and fall through the liquid iron, driven by temperature differences between the scorching inner core and the relatively cooler core mantle boundary 300 kilometers above. These cells persist for millions of years, slowly circulating molten metal through paths that spiral around Earth's rotation axis like enormous helical rivers flowing through three-dimensional space. The Coriolis force, that same deflecting influence that will eventually shape weather patterns and ocean currents on Earth's surface, organizes these convective motions into columns aligned roughly parallel to the planet's rotation axis. Each column extends through the entire thickness of the outer core, creating a structure that resembles a vast metallic forest where the trees are currents of flowing iron and the forest floor lies nearly 3,000 kilometers beneath the surface. These columnar flows stretch and amplify magnetic field lines through a process that operates according to the same physical principles governing dynamos in human-built generators, except scaled up to planetary dimensions and powered by the heat of Earth's formation and the ongoing crystallization of the solid inner core. The mathematics describing this geodynamo process involve equations that couple fluid dynamics, thermodynamics, and electromagnetism in ways that challenge even modern supercomputers. The Reynolds number, a dimensionless parameter that characterizes the turbulent nature of fluid flow, reaches values in Earth's core that exceed those found in any laboratory experiment by factors of millions. The magnetic Reynolds number, which describes how magnetic field lines become trapped and amplified in moving conductors, similarly reaches extreme values that place Earth's core dynamo in a regime where small changes can have enormous consequences. Yet somehow, despite this underlying chaos, the geodynamo stabilizes into a configuration that produces a remarkably steady magnetic field. The field resembles, to first approximation, that of a giant bar magnet tilted about 11 degrees from Earth's rotation axis, with field lines emerging from the southern magnetic pole, curving through space in graceful arcs, and re-entering the planet near the northern magnetic pole. This dipole field contains roughly 80% of the total magnetic energy, while the remaining 20% resides in smaller scale features that reflect the complex turbulence occurring in the outer core. Scientists studying the geodynamo have discovered that the system exhibits what they call dipole dominance, the tendency for the large-scale dipole field to suppress smaller-scale magnetic instabilities that might otherwise disrupt the dynamo process. This dominance emerges naturally from the geometry of core convection and the constraints imposed by Earth's rotation, creating a self-regulating mechanism that maintains magnetic field strength within a relatively narrow range over geological timescales. Only took the planet about 500 million years to achieve this stable configuration, roughly the same time required for the first oceans to form and persist. The inner core plays a crucial role in this stabilization process, even though it remains solid and cannot participate directly in the convective motions that generate the magnetic field. As the planet slowly cools over geological time, iron crystallizes onto the inner core boundary, releasing latent heat that drives thermal convection in the overlying liquid. This crystallization process also excludes lighter elements, primarily sulfur, oxygen, and silicon from the solid iron crystal lattice, creating compositional buoyancy that enhances convective motions in the outer core. Seismic studies suggest that Earth's solid inner core began forming relatively recently in the planet's history, perhaps within the last 1.5 billion years. Before the inner core existed, the geodynamo operated through thermal convection alone, driven by heat escaping from the core through the overlying mantle. The addition of compositional convection when the inner core began crystallizing may have strengthened and stabilized Earth's magnetic field, possibly explaining why complex multicellular life appeared around the same time the magnetic field became strong enough to provide more effective protection against harmful cosmic radiation. The transition from purely thermal to thermochemical convection represents one of the most significant changes in Earth's internal dynamics since the planet's formation. Computer simulations suggest that this transition initially caused the magnetic field to fluctuate dramatically, with field strength varying by factors of 10 and magnetic poles wandering across the planet's surface before settling into the more stable configuration observed today. Paleomagnetic records from rocks formed during this transition period show evidence of rapid changes in field direction and intensity, supporting the idea that Earth's magnetic field experienced a major reorganization when the inner core began to form. The dynamo process also exhibits long-term variations that operate on timescales ranging from decades to millions of years. Satellite measurements over the past few decades reveal that Earth's magnetic field is currently weakening at a rate of about 5% per century, while the magnetic poles drift across the planet's surface at speeds of tens of kilometers per year. These changes reflect ongoing adjustments in core convection patterns, as temperature and compositional gradients evolve in response to the planet's continued cooling and the growth of the inner core. Some of these variations may be cyclical, driven by interactions between different modes of convection in the outer core. The Atlantic and Pacific hemispheres appear to exhibit different magnetic field behaviors, with the field weakening more rapidly under the South Atlantic while strengthening slightly under the Pacific. This asymmetry may reflect the influence of lower mantle structure on core convection, as temperature variations at the core mantle boundary create preferred pathways for rising and sinking ion flows. The geodynamo's stability has profound implications for the development of life on Earth's surface. Without a strong magnetic field to deflect most cosmic radiation and solar wind particles, Earth's atmosphere would gradually be stripped away by solar heating and electromagnetic forces, following the same path taken by Mars after its magnetic field weakened and eventually disappeared. Venus, despite its similar size and composition to Earth, generates no global magnetic field and consequently possesses an atmosphere dominated by carbon dioxide at crushing pressures and temperatures exceeding 460 degrees Celsius. Only took evolution nearly 4 billion years to produce observers capable of recognizing that their planet's habitability depends on invisible processes occurring at depths greater than the distance from New York to Los Angeles. Processes that convert thermal energy into electromagnetic protection through mechanisms that operate according to physical laws discovered only within the past few centuries. The geodynamo continues its quiet revolution, indifferent to the life it protects, unaware that its magnetic field makes possible the complex chemistry occurring in Earth's biosphere. The same complex chemistry that eventually developed sufficient sophistication to study the planetary dynamo and marvel at its elegant operation. The convection patterns that sustain this magnetic field will persist for billions of years, gradually changing as Earth's interior cools and the inner core grows larger, but maintaining their essential function of converting planetary heat into electromagnetic force. In this sense, Earth's magnetic field represents one of the most successful experiments in planetary engineering, a system that has operated continuously for most of Earth's history, protecting an entire world and enabling the evolution of life forms complex enough to contemplate their own magnetic origins. Magnetic poles begin their wander across Earth's surface like slow travelers, following invisible paths through a landscape that exists only in the mathematics of electromagnetic force. Tracing routes that curve and meander according to the turbulent patterns of convection occurring thousands of kilometers beneath the solid ground. The North Magnetic Pole, that point where Earth's magnetic field lines dive vertically downward into the planet's interior, drifts across the Canadian Arctic at speeds that vary from a few kilometers per year to as much as 60 kilometers per year, depending on changes in the convection patterns driving the geodynamo deep within the outer core. This wandering represents one of the most visible manifestations of the dynamic processes occurring in Earth's liquid iron heart, a surface expression of the complex fluid motions that generate and maintain the planet's magnetic field. Unlike geographic poles, which mark the endpoints of Earth's rotation axis and remain fixed relative to the planet's surface features, magnetic poles move continuously in response to evolving patterns of core convection, following currents in molten iron that shift like weather systems made of metal flowing at temperatures exceeding those found on the Sun's surface. The North Magnetic Pole's journey can be traced through historical records of magnetic declination, the angle between magnetic north and true north, measured by compass needles at various locations around the world. Early Arctic explorers, navigating by magnetic compass across landscapes where magnetic declination changes dramatically over short distances, unknowingly documented the pole's location through their navigation records. James Clark Ross first reached the North Magnetic Pole in 1831, finding it located on the Boothia Peninsula in what is now northern Canada, roughly 1,600 kilometers south of the geographic North Pole. Since that first direct measurement, the North Magnetic Pole has traveled more than 2,300 kilometers across the Canadian Arctic, following a northwest trajectory that carried it from the Boothia Peninsula through the Canadian Arctic archipelago and into the Arctic Ocean. Its speed has increased dramatically over the past several decades, accelerating from roughly 10 kilometers per year in the early 1900s to more than 50 kilometers per year by the early 21st century, a pace that, if sustained, would carry the pole from northern Canada to Siberia within a human lifetime. This acceleration reflects changes in the strength and geometry of convective flows in Earth's outer core, particularly in the region beneath northern Canada, where magnetic field lines associated with the North Magnetic Pole originate. Computer simulations of core dynamics suggest that the pole's rapid movement results from competing influences of different convection cells, with a strengthening cell beneath Siberia beginning to dominate over a weakening cell beneath Canada. Only took geophysicists until the 1990s to realize that magnetic pole motion could accelerate so dramatically within a human lifetime. The South Magnetic Pole exhibits its own independent wandering pattern, currently located off the coast of Antarctica in the Southern Ocean, roughly 2,800 kilometers from the geographic South Pole. Its motion follows a different trajectory than its northern counterpart, reflecting the asymmetric nature of convection in Earth's outer core and the influence of varying heat flow patterns at the core mantle boundary. While the North Magnetic Pole races towards Siberia, the South Magnetic Pole moves more slowly across the oceanic regions surrounding Antarctica, tracing loops and curves that sometimes reverse direction as competing convection cells wax and wane in intensity. The relationship between magnetic pole motion and core convection reveals itself most clearly in the mathematical models that describe how magnetic field lines emerge from Earth's interior. Each pole represents a point where the planet's magnetic field becomes vertical, diving straight down into the core or emerging straight up from it. The location of these points depends on the detailed three-dimensional structure of the magnetic field, which in turn reflects the complex geometry of convective flows in the liquid outer core. Small changes in convection patterns can cause magnetic field lines to tilt, shifting the locations where they become vertical and thus moving the magnetic poles across Earth's surface. Paleomagnetic studies of ancient rocks reveal that magnetic poles have wandered throughout Earth's history, sometimes following predictable paths, sometimes moving erratically as the geodynamo adjusts to changing conditions in the planet's interior. During periods of stable magnetic field configuration, pole motion tends to be relatively slow and steady, During times of magnetic instability, periods when the field strength weakens, or when magnetic reversals approach pole motion, can become rapid and chaotic, with poles sometimes moving thousands of kilometers in geologically brief intervals. The wandering poles create practical challenges for navigation systems that rely on magnetic compass readings. Airports must regularly update their runway numbering systems, which are based on magnetic headings, to account for changing magnetic declination as the magnetic poles drift. The magnetic declination at any given location changes continuously as the poles move, requiring periodic updates to nautical and aeronautical charts used for navigation. In regions near the magnetic poles, where magnetic declination changes most rapidly, these updates may be required annually or even more frequently. Scientists tracking pole motion use a global network of magnetic observatories, each equipped with sensitive magnetometers that continuously monitor the strength and direction of Earth's magnetic field. These observations, combined with magnetic field measurements from satellites orbiting hundreds of kilometers above Earth's surface, allow researchers to create detailed maps of how the magnetic field changes over time and to predict future pole positions with reasonable accuracy over periods of several years. The predictions become less reliable over longer timescales because magnetic pole motion depends on convection patterns in the outer core that exhibit chaotic behavior similar to weather systems in Earth's atmosphere. Just as meteorologists cannot predict specific weather conditions more than a week or two in advance, geophysicists cannot predict exactly where magnetic poles will be located decades in the future. They can, however, identify general trends and estimate the range of likely future positions based on current motion patterns and understanding of core dynamics. Magnetic pole wandering also affects the distribution of cosmic ray particles that manage to penetrate Earth's magnetic field and reach the upper atmosphere. These high-energy particles, mostly protons accelerated by supernova explosions in distant parts of the galaxy, follow magnetic field lines as they approach Earth, with most being deflected harmlessly into space. However, some particles reach the atmosphere near the magnetic poles, where field lines funnel downward into the planet's interior. As the magnetic poles move, they carry these cosmic ray entry points along with them, subtly altering the geographic distribution of cosmic ray bombardment over time scales of decades and centuries. The aurora zones, roughly circular regions centered on the magnetic poles where aurora displays occur, most frequently drift along with the poles themselves. Northern Canada, which experienced regular aurora displays when the magnetic pole was located nearby, now sees fewer aurora as the pole moves towards Siberia. Conversely, regions of Siberia that historically experienced fewer aurora now find themselves in the expanding northern aurora zone as the magnetic pole approaches their longitude. Only took the aurora a few decades to begin relocating from Canada toward Russia. This migration of aurora zones represents a visible reminder that Earth's magnetic field remains dynamic and evolving, shaped by processes occurring deep within the planet's interior that operate on timescales ranging from years to millions of years. The wandering magnetic poles serve as surface expressions of the geodynamo's continuing adjustment to changing conditions in the outer core. Ambassadors from the metallic depths carrying news of thermal and compositional currents that flow through liquid iron at pressures exceeding those found at the bottom of ocean trenches and temperatures that match the surface of the sun. Solar maximum's ancient fury erupts from the sun's surface with a violence that dwarfs terrestrial storms, hurricanes, and volcanic explosions combined, launching billion-ton clouds of magnetized plasma into interplanetary space at velocities that compress the normal 3-day journey from Sun to Earth into mere hours. During these periods of peak solar activity, which occur roughly every 11 years when the sun's magnetic field reaches maximum complexity and instability, Massive solar flares release energy equivalent to billions of hydrogen bombs detonating simultaneously, while coronal mass ejections hurl magnetized plasma across the solar system with enough momentum to strip atmospheres from unprotected planets. The young sun, burning with fiercer magnetic intensity than its modern counterpart, experiences solar maxima that exceed contemporary storms by factors of 10 or more. Its faster rotation, perhaps spinning once every few days rather than the current 27-day period, generates magnetic fields twisted into configurations so complex that they inevitably snap apart in catastrophic reconnection events that illuminate the entire solar corona. These ancient solar storms, occurring during Earth's first billion years when the planet's magnetic field was still finding its stable configuration, bombard the magnetosphere with pressures and particle fluxes that compress Earth's protective magnetic bubble to its absolute limits. When a major coronal mass ejection approaches Earth during solar maximum, it carries with it a twisted bundle of magnetic field lines frozen into the plasma like DNA strands, preserving information about the sun's magnetic state at the moment of eruption. The magnetic orientation of this approaching cloud determines how severely it will interact with Earth's magnetosphere if the embedded magnetic field points southward. Opposite to Earth's northward pointing field, in the region where they meet, magnetic reconnection occurs with explosive efficiency, allowing solar wind particles to penetrate deep into the magnetosphere and triggering the most intense magnetic storms in Earth's electromagnetic experience. These reconnection events unfold at the magnetopores with a suddenness that seems impossible given the vast scales involved, yet they obey the same physical principles that govern lightning strikes and electric arcs in laboratory experiments. Magnetic field lines from the Sun and Earth approach each other, touch, and suddenly merge, snapping apart like overstretched rubber bands and releasing energy that accelerates charged particles to speeds approaching those of cosmic rays. The process occurs across regions hundreds of kilometers wide and happens within minutes or even seconds. Despite involving magnetic structures that extend across millions of kilometers of space, the particle acceleration triggered by these reconnection events creates radiation environments around Earth that rival those found in the heart of particle accelerators, except spread across volumes larger than entire planets. Electrons gain energies exceeding 1 million electron volts, while protons acquire speeds that carry them from the magnetosphere's outer boundary to the upper atmosphere in less than an hour. These energetic particles, guided by Earth's magnetic field lines, converge on the polar regions where they create aurora displays visible across entire continents, painting the sky in curtains of light that ripple and dance for days without interruption. During the most severe ancient solar storms, the aurora zones expand far beyond their normal polar confines, reaching magnetic latitudes that correspond to regions where temperate forests will eventually grow and civilizations will build their cities. The magnetic field lines that normally confine aurora to high latitudes become so distorted by the pressure of incoming solar wind that they carry energetic particles deep into regions normally protected from such bombardment. Observers at tropical latitudes, had any existed, would witness aurora displays overhead, an impossible sight under normal magnetic conditions, yet routine during the extreme solar storms of Earth's youth. The electromagnetic pulses generated by these ancient magnetic storms induce electric currents in any conducting material they encounter on Earth's surface or in its oceans. The newly formed oceanic basins, containing seawater with dissolved salts that make it electrically conductive, experience current flows measured in millions of amperes as the changing magnetic fields from space interact with terrestrial conductors, according to Faraday's law of electromagnetic induction. These geomagnetically induced currents heat the water slightly and drive electrochemical reactions that may contribute to the complex chemistry occurring in Earth's early oceans. The storms also compress Earth's magnetosphere so dramatically that its boundary approaches within 20,000 kilometers of the planet's surface, roughly half the distance to the Moon and closer than modern geostationary satellites orbit. At this compressed configuration, the magnetosphere's ability to deflect solar wind particles becomes severely compromised, allowing unprecedented quantities of solar plasma to penetrate the upper atmosphere and interact with whatever gases comprise Earth's early atmospheric composition. Only took these extreme solar storms a few 100 million years to help shape the chemical evolution of Earth's atmosphere. Solar maximum periods during the Sun's youth may have lasted longer than the modern 11-year cycle, with some evidence suggesting that early solar activity followed patterns measured in decades rather than years. The young Sun's magnetic field, generated by convection patterns in a stellar interior, hotter and more turbulent than today's solar core, exhibited greater instability and produced magnetic configurations that modern solar physics struggles to model accurately. Sunspot numbers during ancient solar maxima may have reached values 10 times higher than those recorded during the most active periods of recent centuries. The frequency of major coronal mass ejections during these ancient solar maxima approaches 1 per day during peak activity, compared to perhaps 1 per week during modern solar maximum periods. Each ejection carries magnetic field strengths and particle densities that exceed contemporary values by substantial margins, creating a nearly continuous bombardment of Earth's magnetosphere by magnetized plasma clouds traveling at speeds up to 2,000 kilometers per second, nearly 3 times faster than typical modern solar wind velocities. Between the arrival of successive coronal mass ejections, Earth's magnetosphere attempts to recover its normal configuration, but the recovery time required exceeds the interval between storm arrivals, creating a state of chronic magnetic disturbance that persists for months or years during particularly active solar periods. The magnetosphere develops a battered, asymmetric shape as it struggles to maintain its protective function against the relentless solar assault, with magnetic field lines stretched and twisted into configurations that barely resemble the elegant dipole geometry that characterizes quiet periods. These prolonged magnetic storms trigger atmospheric chemistry that would not occur under normal conditions, driving reactions between nitrogen, oxygen, carbon dioxide, and water vapor at altitudes where temperatures and pressures create unique chemical environments. Some of the molecular species produced by storm-enhanced atmospheric chemistry rain down onto Earth's surface, adding to the inventory of complex molecules available for the eventual emergence of life. The storms thus serve a dual function, protecting the planet from the worst effects of solar radiation while simultaneously contributing to the chemical processes that make biochemistry possible. The ancient solar storms also generate radio emissions across a broad range of frequencies, filling the space around Earth with electromagnetic noise that would overwhelm modern communication systems but simply adds to the natural radio background of the early solar system. These radio waves, produced by accelerated electrons spiraling along magnetic field lines, carry information about the storm's intensity and magnetic geometry across interplanetary distances, creating a kind of electromagnetic lighthouse that broadcasts news of solar activity to any planet with instruments sensitive enough to detect and decode the signals. Only took solar maximum about 4 billion years to establish the cyclical pattern of magnetic storms and recoveries that continues to influence Earth's magnetosphere today, a rhythm of electromagnetic violence and restoration that has persisted through the rise and fall of mountain ranges, the opening and closing of ocean basins, the evolution of life from simple cells to complex ecosystems, all occurring under the protection of a magnetic field that learned to survive the sun's fiercest tantrums and emerge stronger from each encounter with ancient solar fury. The core's crystalline secret lies buried at Earth's center, deeper than any drill has ever penetrated, deeper than any earthquake wave can clearly illuminate. In a realm where pressures exceed 360 billion pascals, more than 3 million times, atmospheric pressure and temperatures rival those found in the outer layers of stars. Here, at the very heart of the planet, solid iron grows with infinite patience, crystallizing from liquid metal one atom at a time, releasing latent heat that drives the convective motions responsible for generating Earth's protective magnetic field. This innermost sphere, roughly 1,220 kilometers in radius, about the size of Pluto, represents one of the most inaccessible yet crucial components of Earth's magnetic defense system. The process of crystallization at Earth's center unfolds according to principles that govern phase transitions throughout the universe. Yet the specific conditions within the inner core create an environment unlike anywhere else in the solar system. At the inner core boundary, where solid iron meets liquid iron, temperatures reach approximately 200 degrees Celsius, comparable to the surface temperature of the Sun, while pressures compress matter to densities exceeding 13 grams per cubic centimeter, nearly twice the density of lead at Earth's surface. Under these extreme conditions, iron atoms arrange themselves into crystalline structures that follow the same geometric principles governing snowflakes and salt crystals, but compressed and heated beyond any terrestrial experience. Seismic studies using earthquake waves that travel through Earth's interior suggest that the inner core consists primarily of an iron-nickel alloy organized into a hexagonal, close-packed crystal structure. Though some evidence points toward a body-centered cubic arrangement in certain regions, the uncertainty reflects the extraordinary difficulty of probing conditions that exceed those achievable in any laboratory experiment, forcing scientists to rely on indirect observations and theoretical calculations based on quantum mechanical models of matter under extreme compression. Only took seismologists until the 1930s to prove that Earth possesses a solid inner core, and they are still debating its precise composition and structure. The crystallization process itself releases energy in the form of latent heat, the same phenomenon that warms the air when water vapor condenses into raindrops, but here operating at temperatures that would vaporize any known material at surface pressures. As each iron atom joins the growing crystal lattice of the inner core, it gives up the kinetic energy associated with its liquid state, converting motion into thermal energy that must escape through the overlying liquid outer core. This heat flow drives thermal convection in the outer core, creating temperature differences that help sustain the convective motions responsible for generating Earth's magnetic field. But the crystallization process involves more than simple solidification of liquid iron. The crystal lattice of solid iron cannot accommodate all the lighter elements, primarily sulfur, oxygen, silicon, and possibly hydrogen, that remain dissolved in the liquid outer core. As iron crystallizes onto the inner core boundary, these lighter elements are excluded from the solid phase and accumulate in the adjacent liquid, creating compositional gradients that generate additional buoyancy forces. This compositionally driven convection supplements thermal convection, providing an additional energy source for the geodynamo that may be more efficient at generating magnetic fields than thermal convection alone. The growth rate of the inner core depends on the rate at which Earth's interior loses heat to space through the slow process of mantle convection and crustal cooling. Current estimates suggest that the inner core grows by roughly 1 millimeter per year as the planet gradually cools from its initial molten state, a pace so slow that the core's radius has increased by only about 300 kilometers since complex life began evolving in Earth's oceans. At this rate, the inner core began forming sometime between 1 and 1.5 billion years ago, relatively recently in Earth's 4.6 billion year history. suggesting that the geodynamo operated through purely thermal convection for most of the planet's existence. The transition from a purely liquid core to one containing a solid inner region may have triggered significant changes in Earth's magnetic field behavior. Computer simulations suggest that the onset of inner core crystallization initially destabilized the geodynamo, causing magnetic field strength to fluctuate wildly and magnetic reversals to occur more frequently before the system adjusted to its new configuration. Paleomagnetic evidence from rocks formed during the Proterozoic eon, around the time when inner core formation likely began, shows signs of increased magnetic field variability consistent with this theoretical prediction. The solid inner core also exhibits rotational behavior that differs from the rest of the planet, a phenomenon discovered through careful analysis of seismic waves that travel through the core and emerge on the opposite side of Earth. These waves reveal that the inner core rotates slightly faster than Earth's surface, completing an extra revolution roughly every 120 years, a phenomenon called superrotation that reflects the complex interaction between the solid inner core and the flowing liquid outer core that surrounds it. The superrotation rate varies over time, sometimes accelerating, sometimes slowing, in response to changes in the electromagnetic forces generated by core convection. This differential rotation creates additional complications for understanding core dynamics and magnetic field generation. The relative motion between the solid inner core and liquid outer core generates electromagnetic forces that influence convection patterns in the outer core, which in turn affect the magnetic field structure, which feeds back to influence the forces acting on the inner core. These feedback loops create a complex system that challenges attempts to model core behavior over long-time scales, contributing to the chaotic nature of magnetic field variations and the difficulty of predicting magnetic reversals. The crystalline structure of the inner core itself may not be uniform throughout its volume. Seismic evidence suggests that the innermost regions of the inner core, which crystallized first and have had the longest time to adjust to extreme pressure and temperature conditions, may have a different crystal structure than the outer regions that crystallized more recently. Some models propose that the very center of Earth consists of a distinct phase of iron-nickel alloy, with properties that differ from the surrounding material, creating a core within the core that adds another layer of complexity to an already intricate system. The magnetic field generated by convection in the liquid outer core must somehow organize itself around the presence of this solid inner core, creating field lines that thread through liquid metal while avoiding the solid obstacle at the center. The interaction between the magnetic field and the electrically conducting inner core generates eddy currents within the solid iron, which produce their own magnetic fields that interact with the primary field generated by outer core convection. These electromagnetic interactions help couple the motion of the liquid and solid regions of the core, transferring angular momentum and energy between different parts of Earth's interior. Recent research suggests that the inner core may not be perfectly solid throughout its volume, but instead may contain regions of partial melting where temperature and pressure conditions hover near the boundary between solid and liquid phases. These mushy zones, if they exist, would create additional complexity in the heat transfer and electromagnetic processes occurring at Earth's center, potentially affecting the efficiency of magnetic field generation and the long-term evolution of the geodynamo system. The chemical composition of the inner core remains uncertain despite decades of research, with ongoing debates about the identity and abundance of light elements mixed with iron and nickel in the crystalline lattice. Experimental studies at extreme pressures and temperatures suggest that oxygen, sulfur, silicon, and carbon can all dissolve in solid iron under core conditions. But the relative proportions of these elements and their effects on inner core properties remain subjects of active investigation. Only took planetary science about 90 years to realize that Earth's core consists of more than pure iron, and researchers are still working to determine exactly what else might be hidden in the crystalline secret at our planet's heart. The inner core continues growing with each passing year, slowly consuming the liquid outer core from within while releasing the latent heat and compositional buoyancy that sustain the geodynamo. This process will continue for billions of years until the entire core solidifies, at which point Earth's magnetic field will weaken and eventually disappear, following the same path taken by Mars when its smaller core cooled enough to shut down its magnetic dynamo. Until then, the crystalline secret at Earth's center continues its patient work of protecting the planet's surface from cosmic radiation, one iron atom at a time. Magnetic reversal's gentle chaos unfolds across Earth's surface with the quiet inevitability of seasons changing, except measured not in months, but in hundreds of thousands of years, as the planet's magnetic field gradually weakens, falters, and then rebuilds itself with opposite polarity, north becoming south, south becoming north in a process so gradual that no single generation of any species would notice the transition occurring. These reversals represent one of the most dramatic yet peaceful transformations in Earth's geophysical behavior, periods when the magnetic field that has protected life for billions of years temporarily abandons its post, leaving the planet's atmosphere exposed to cosmic radiation and solar wind bombardment while the geodynamo deep in the outer core reorganizes itself according to new patterns of convection. The geological record preserved in ancient rocks reveals that magnetic reversals have occurred throughout Earth's history with frequencies that vary dramatically over time. During some periods, the magnetic field maintains stable polarity for tens of millions of years. The Cretaceous normal superchron lasted approximately 40 million years without a single reversal, while dinosaurs evolved, flourished, and eventually disappeared under the protection of a magnetic field that pointed consistently in the same direction. During other periods, reversals occur as frequently as every few thousand years, creating a rapid staccato of magnetic instability that challenges life's ability to adapt to changing levels of cosmic radiation exposure. The current magnetic field configuration, with magnetic north roughly aligned with geographic north, has persisted for approximately 780,000 years, a period known as the Brunhes normal chron, named after the French geophysicist Bernard Brunhes, who first recognized evidence of magnetic reversals in volcanic rocks. This represents a moderately long interval of magnetic stability. Though not exceptional by geological standards, statistical analysis of paleomagnetic records suggests that reversals occur on average every 200,000 to 300,000 years, but with enormous variability, some intervals between reversals last only 20,000 years, while others extend beyond 50 million years. The reversal process itself unfolds over thousands of years as competing regions of magnetic field generation in Earth's outer core struggle for dominance. Computer simulations of geodynamo behavior reveal that reversals often begin when patches of reverse polarity develop at the core mantle boundary, growing and strengthening until they begin to influence the overall field configuration. These reverse flux patches can persist for millennia before either dissipating or expanding to overwhelm the existing dipole field, creating a complex competition between old and new magnetic field structures that plays out across timescales that dwarf human civilization. During the transition period, Earth's magnetic field weakens to perhaps 10% of its normal strength, while the simple dipole configuration that normally characterizes the field degenerates into a complex, multipolar structure with magnetic poles scattered across the planet's surface, like compass needles gone haywire. Paleomagnetic studies of lava flows that cooled during ancient reversals reveal magnetic directions that point in seemingly random directions, reflecting the chaotic field geometry that exists during these transitional periods. Only took paleomagnetists until the 1960s to realize that these apparently random directions actually record the complex magnetic field behavior during reversals. The weakened magnetic field during reversals allows increased cosmic radiation to reach Earth's upper atmosphere, where high-energy particles from distant supernovae and galactic sources interact with atmospheric molecules to produce cascades of secondary particles and increased levels of cosmogenic isotopes such as carbon-14 and beryllium-10. Ice cores from Greenland and Antarctica preserve records of these isotope spikes, providing independent evidence of past magnetic field variations and helping scientists correlate paleomagnetic records with other geological and climatological data. Some researchers have proposed that magnetic reversals correlate with mass extinction events in Earth's fossil record, suggesting that increased cosmic radiation during periods of weakened magnetic protection might stress ecosystems and contribute to species loss. However, the evidence for such correlations remains controversial, with most studies finding only weak relationships between reversal timing and extinction events. Life has survived hundreds of magnetic reversals over the past several hundred million years, suggesting remarkable resilience to the temporary loss of magnetic protection. Perhaps because Earth's atmosphere provides secondary shielding against most cosmic radiation even when the magnetic field weakens. The mechanism triggering magnetic reversals remains one of the outstanding mysteries in geophysics. Despite decades of research using increasingly sophisticated computer models of core dynamics, the models reveal that reversals emerge naturally from the chaotic nature of turbulent convection in Earth's outer core, where small changes in temperature, composition, or flow patterns can cascade into large-scale reorganizations of the magnetic field structure. The timing of reversals appears fundamentally unpredictable beyond statistical averages, similar to the inherent unpredictability of weather systems despite our detailed understanding of atmospheric physics. Recent paleomagnetic studies have identified precursor signals that sometimes occur decades to centuries before full reversals, including rapid changes in magnetic pole positions, unusual variations in field intensity, and the development of non-dipolar field features at Earth's surface. These precursors suggest that the reversal process may begin with instabilities in specific regions of the outer core that gradually spread and intensify until they trigger a complete reorganization of the global magnetic field. However, not all periods of magnetic instability lead to reversals. The field sometimes recovers its original configuration after brief excursions toward reversed polarity. The South Atlantic anomaly, a region where Earth's magnetic field is currently much weaker than normal, represents a possible precursor to a future reversal or perhaps an aborted reversal attempt. Satellite measurements reveal that this anomaly has been growing and intensifying over the past several centuries, while the overall dipole field strength has decreased by approximately 10% over the past 150 years. Some scientists interpret these changes as early signs of an approaching reversal, while others argue that they represent normal variations in geomagnetic field behavior that will eventually stabilize without triggering a polarity change. The aurora borealis and aurora australis, those ethereal displays of light that currently occur primarily at high magnetic latitudes, would behave very differently during magnetic reversals. The complex, multipolar field geometry that characterizes transitional periods would create multiple aurora zones scattered across the planet's surface, with possible aurora displays occurring at tropical and mid-latitude regions that normally remain far from the aurora zones. Ancient aurora would paint the sky in patterns that follow the twisted, chaotic magnetic field lines characteristic of reversal periods, creating light displays unlike anything witnessed during periods of stable dipole field configuration. The magnetic field lines themselves, normally organized into the elegant loops that connect north and south magnetic poles through graceful arcs extending far into space, become tangled and twisted during reversals like invisible spaghetti stirred by giant hands operating on planetary scales. Some field lines close entirely within Earth's core mantle boundary region, while others stretch chaotically into space before reconnecting with the planet at unexpected locations, creating a magnetosphere so distorted that it barely resembles the organized, dipolar structure that characterizes normal periods. Navigation by magnetic compass becomes impossible during the height of magnetic reversals, when local magnetic directions change from day to day as the chaotic field structure evolves. Migratory animals that rely on magnetic navigation, sea turtles, birds, and bacteria that contain magnetite crystals must somehow adapt to temporary loss of their primary directional reference, perhaps falling back on alternative navigation methods based on celestial cues, polarized light patterns, or other environmental signals that remain stable during magnetic field transitions. Only took the geomagnetic field about 4 billion years to establish the reversal pattern that continues today, a rhythm of stability and chaos that reflects the fundamental nature of the turbulent dynamo process operating in Earth's liquid core. The gentle chaos of magnetic reversals represents one of Earth's most profound yet subtle transformations, occurring so gradually that even the most sensitive organisms adapt without catastrophic disruption, demonstrating the remarkable ability of planetary systems to undergo dramatic change while maintaining the essential functions that support life. Aurora's primordial dance begins at the edge of space, where Earth's magnetosphere captures charged particles accelerated by magnetic reconnection events occurring millions of kilometers away at the boundary between solar wind and terrestrial magnetic fields. These particles, primarily electrons and protons stripped from hydrogen atoms by the sun's intense heat, follow invisible highways carved from magnetic force, spiraling along field lines that guide them toward the polar regions with the precision of trains following rails. Except these rails consist of nothing more substantial than organized electromagnetic fields threading through the vacuum of space. The particles arrive at Earth's upper atmosphere, traveling at velocities that exceed 20,000 kilometers per second for the most energetic electrons, carrying kinetic energy acquired during their acceleration through magnetic reconnection zones where opposing magnetic fields meet, merge, and explosively separate. As they penetrate the thin gases that mark the boundary between Earth and space, roughly 100 to 400 kilometers above the solid surface, they begin colliding with atmospheric molecules, primarily nitrogen and oxygen, during Earth's modern era. But different combinations of gases during the planet's ancient history, when the atmosphere contained little free oxygen and substantial amounts of carbon dioxide, methane, and water vapor, each collision between an incoming charged particle and an atmospheric molecule transfers energy according to the fundamental principles of quantum mechanics, exciting electrons within the molecule to higher energy states where they exist for brief moments before cascading back to their ground states and emitting photons of specific wavelengths determined by the molecular structure involved in the collision. Oxygen atoms produce the characteristic green light at 557, 7 nanometers that dominates many aurora displays, along with red emissions at 630.0 and 636.4 nanometers that appear at higher altitudes, where oxygen atoms have more time to emit their delayed red photons before colliding with other particles. Nitrogen molecules contribute blue and purple hues to the aurora palette through emissions at 427, 8 nanometers and longer wavelengths extending into the red portion of the spectrum, while ionized nitrogen adds magenta and pink colors through transitions that occur after the molecule has lost one of its electrons to the energetic particle bombardment. The specific colors that appear in any given aurora display depend on the energy spectrum of the incoming particles, the altitude where collisions occur, and the density and composition of atmospheric gases at that altitude, creating a complex interplay between solar physics, magnetospheric dynamics, and atmospheric chemistry. During Earth's early history, when the atmosphere contained negligible amounts of free oxygen but substantial concentrations of carbon dioxide and other trace gases, aurora displays would have painted the sky in colors largely absent from modern aurora. Carbon dioxide molecules emit infrared radiation when excited by particle bombardment, creating aurora displays that would appear dim or invisible to human eyes, adapted to visible light, but would blaze brilliantly when viewed through infrared detectors. Water vapor contributes emission lines throughout the near-infrared spectrum, while methane produces complex molecular spectra that would create aurora colors never seen during Earth's oxygen-rich era. The geometry of aurora displays reflects the three-dimensional structure of Earth's magnetic field, which funnels incoming particles toward oval-shaped regions centered on the magnetic poles. These aurora ovals expand and contract in response to changes in solar wind conditions and magnetospheric dynamics, growing larger during magnetic storms when enhanced particle precipitation extends the aurora zones toward lower latitudes, sometimes reaching magnetic latitudes as low as 40 degrees during the most severe geomagnetic disturbances latitudes that correspond to regions where major cities now exist. The curtain-like structure that characterizes many aurora displays results from the interaction between incoming particle beams and magnetic field lines that converge toward the polar regions. Each curtain marks a region where particles following a particular set of magnetic field lines encounter the atmosphere simultaneously, creating aligned sheets of luminosity that stretch across hundreds of kilometers of sky while maintaining widths measured in mere kilometers. These curtains ripple and wave as the magnetic field lines themselves move in response to changing conditions in the magnetosphere, creating the flowing, dancing motion that gives aurora their ethereal character. The altitude at which aurora occur depends on the energy of the incoming particles and the density profile of the atmosphere. Low-energy particles, typically those with energies less than 10,000 electron volts, penetrate only to altitudes above 200 kilometers, where the atmosphere remains extremely thin and composed primarily of atomic oxygen. Higher energy particles can penetrate deeper, creating aurora displays at altitudes as low as 80 kilometers, where they encounter denser concentrations of molecular nitrogen and oxygen, though such deep penetration requires particle energies exceeding 100,000 electron volts, which occur only during the most intense magnetic storms. Scientists studying aurora phenomena have discovered that the displays exhibit fine structure on scales ranging from meters to thousands of kilometers, with individual aurora rays sometimes measuring less than 100 meters in width, while extending vertically through tens of kilometers of atmosphere. This fine structure reflects the complex magnetic field geometry that guides particle precipitation, including magnetic field-aligned currents that flow between the magnetosphere and ionosphere, creating preferential pathways for particle precipitation that appear as discrete aurora rays when viewed from the ground. The temporal behavior of aurora displays ranges from slowly evolving background glows that persist for hours to rapidly flickering structures that change on timescales of seconds or fractions of seconds. The fastest aurora variations, sometimes called flickering aurora, occur when the magnetosphere becomes unstable and generates bursts of particle precipitation lasting only milliseconds. These rapid variations require high-speed cameras to capture properly and reveal dynamics in the magnetosphere-ionosphere system that operate on timescales comparable to lightning discharges, though the physical mechanisms involved differ completely from atmospheric electricity. Paleomagnetic evidence suggests that ancient aurora occurred at different latitudes than modern displays due to changes in the magnetic pole positions and magnetic field strength over geological time. During periods when Earth's magnetic field was weaker than today, aurora ovals expanded toward lower latitudes, bringing aurora displays to regions that now experience them only during extreme magnetic storms. Conversely, during periods of stronger magnetic field, aurora contracted toward higher latitudes, reducing the geographic extent of regions where aurora could be observed. The primordial aurora that illuminated Earth's skies during the planet's first billion years occurred under a sun that produced more intense magnetic storms but less total energy output than the modern sun, creating aurora displays that were simultaneously more frequent and more spectacular than contemporary aurora, but occurred under dimmer background illumination from a young star still settling into its main sequence configuration. Only took aurora about 4 billion years to establish the connection between solar magnetic activity and terrestrial light displays that continues to paint polar skies in colors that span the electromagnetic spectrum. The energy budget of aurora displays involves the conversion of magnetic field energy into particle kinetic energy, then into electromagnetic radiation, with efficiencies that depend on atmospheric composition and particle energy distributions. During major aurora storms, the total power dissipated in Earth's upper atmosphere can exceed 100 billion watts, roughly equivalent to the electrical power consumption of a large country, yet this represents only a tiny fraction of the total energy involved in the magnetospheric processes that drive aurora formation, demonstrating the vast scales of energy transfer occurring during the interaction between solar wind and Earth's magnetic field. Aurora continue their primordial dance today, much as they have for billions of years, following magnetic field lines toward polar regions, exciting atmospheric molecules according to the same quantum mechanical principles that governed their emission spectra when Earth was young, creating displays of light that serve as visible manifestations of invisible processes occurring throughout the solar terrestrial system, painting the sky with colors that tell stories of magnetic reconnection, particle acceleration, and atmospheric chemistry written in wavelengths of light that connect the depths of Earth's magnetosphere with the thin gases that mark the boundary between our planet and the cosmos beyond. The sun's magnetic breathing follows an 11-year rhythm as regular as any heartbeat, yet infinitely more complex in its patterns of expansion and contraction. As the solar magnetic field builds toward maximum complexity through the gradual winding and twisting of field lines by differential rotation, then catastrophically simplifies through explosive releases of stored magnetic energy that reset the cycle and begin the process anew. This solar breathing affects every corner of the solar system, modulating the intensity of solar wind, the frequency of coronal mass ejections, and the particle bombardment that Earth's magnetosphere must deflect or absorb, creating an interplanetary pulse that has regulated space weather for billions of years. The cycle begins during solar minimum, when the sun's magnetic field assumes its simplest configuration, a mostly dipolar structure similar to a bar magnet, with field lines emerging from one polar region, arcing through the corona in graceful loops, and returning to the surface at the opposite pole. Sunspot numbers drop to near zero during these quiet periods, while the solar wind flows at steady velocities around 400 kilometers per second, carrying relatively weak magnetic fields and sparse particle densities across interplanetary space. Earth's magnetosphere expands to its maximum extent during solar minimum, as reduced solar wind pressure allows the magnetic boundaries to relax outward like a balloon inflating in thinner air. But the sun's differential rotation, the phenomenon where solar plasma near the equator rotates faster than plasma near the poles, completing one rotation in about 25 days compared to 35 days at high latitudes, gradually winds the magnetic field lines like rubber bands being twisted by mismatched gears. This differential rotation, driven by convection patterns in the solar interior that transport angular momentum in complex ways, stretches initially north-south magnetic field lines into east-west orientations, concentrating magnetic flux into narrow bands that migrate toward the solar equator as the cycle progresses. The concentrated magnetic flux begins to exhibit buoyancy, rising through the solar interior until it erupts through the photosphere as sunspot pairs regions where intense magnetic fields suppress convective heat transport, creating cooler, darker areas on the solar surface surrounded by brilliant faculae where magnetic field lines emerge and dive back into the solar interior. Each sunspot pair marks the footpoints of a magnetic flux tube that extends high into the corona, creating the complex magnetic architecture that will eventually become unstable and trigger coronal mass ejections. As the solar cycle progresses toward maximum activity, sunspot numbers increase exponentially, sometimes reaching daily counts exceeding 200 individual spots distributed across the solar disk in two bands located roughly 30 degrees north and south of the solar equator. The magnetic field configuration becomes increasingly complex, with opposing magnetic polarities in close proximity creating conditions favorable for magnetic reconnection events that release enormous amounts of stored magnetic energy in the form of solar flares and coronal mass ejections. Solar flares, the most explosive events in the solar system, release energy equivalent to billions of hydrogen bombs in time frames measured in minutes or hours, heating coronal plasma to temperatures exceeding 20 million degrees Celsius and accelerating particles to speeds approaching half the velocity of light. The electromagnetic radiation from major solar flares reaches Earth in approximately 8 minutes, traveling at light speed across the 150 million kilometers separating the two worlds, while the associated coronal mass ejections require 1 to 3 days to traverse the same distance at their more pedestrian velocities of 400 to 2,000 kilometers per second. The particle clouds expelled by coronal mass ejections carry with them samples of the solar corona plasma heated to millions of degrees and magnetized with field strengths that can exceed Earth's surface magnetic field by factors of 100 or more when compressed by their journey through interplanetary space. These magnetic clouds maintain their internal structure during the trip from Sun to Earth, preserving information about solar magnetic field configurations at the moment of eruption, like fossils embedded in streams of charged particles flowing across the solar system. Earth's magnetosphere learns to anticipate these solar magnetic cycles, responding to the gradually changing baseline conditions as solar activity waxes and wanes over the 11-year period. During solar maximum, when coronal mass ejections arrive several times per week, the magnetosphere assumes a more compressed, stressed configuration as it adapts to near constant bombardment by enhanced solar wind conditions. The aurora zones expand toward lower latitudes, bringing displays of polar lights to regions that see them only rarely during solar minimum periods. The galactic cosmic ray flux reaching Earth varies inversely with solar activity levels. As the enhanced magnetic fields and particle densities during solar maximum create more effective barriers against high-energy particles accelerated by distant supernova explosions and other galactic phenomena, this cosmic ray modulation creates an 11-year cycle in the production rates of cosmogenic isotopes, such as carbon-14 and beryllium-10 in Earth's atmosphere, providing an indirect record of past solar activity preserved in tree rings, ice cores, and sediment layers that extends the documented history of solar cycles back thousands of years. Tree ring studies reveal that the 11-year solar cycle has persisted with remarkable consistency throughout recorded history. Though with variations in amplitude and occasionally with longer periods of suppressed activity, such as the Maunder minimum between 1645 and 1715, when sunspot numbers remained abnormally low for several decades. During this period, Earth experienced cooler temperatures associated with the Little Ice Age, demonstrating the connection between solar magnetic activity and terrestrial climate through mechanisms that remain subjects of ongoing research. The physical mechanisms driving the solar magnetic cycle involve the complex interaction between convection, differential rotation, and magnetic field generation in the solar interior, a process that operates according to magneto-hydrodynamic principles similar to those governing Earth's geodynamo, but on vastly different scales of time, space, and energy. The solar dynamo generates magnetic fields through the stretching and twisting of field lines by fluid motions, then periodically reverses the global magnetic polarity when the accumulated magnetic stress exceeds the system's ability to maintain stable configuration. Computer simulations of solar dynamo processes require some of the world's most powerful supercomputers, yet still struggle to reproduce the observed complexity and regularity of the 11-year cycle, highlighting the fundamental challenges involved in modeling turbulent magneto-hydrodynamic systems that span multiple scale lengths from convective cells a few hundred kilometers across to global circulation patterns that encompass the entire solar interior. Only took heliophysicists about 150 years to recognize the solar cycle's regularity and another century to begin understanding the physical processes responsible for its generation. The solar magnetic breathing also exhibits longer-term variations superimposed on the basic 11-year rhythm, including 22-year cycles related to the complete reversal of the Sun's global magnetic polarity, approximately 80-year variations in cycle amplitude called Gleisberg cycles, and possible 200-year oscillations that may correlate with longer-term climate variations on Earth. These longer cycles suggest that the solar dynamo operates with multiple characteristic timescales, creating a complex hierarchy of magnetic variations that influence space weather conditions across the solar system. Other stars exhibit magnetic cycles similar to the Sun's, though with periods ranging from a few years to several decades depending on stellar mass, rotation rate, and convection zone properties. These stellar cycles provide laboratories for testing theories of dynamo processes under different physical conditions, revealing that magnetic breathing represents a fundamental characteristic of stars with convective envelopes and providing context for understanding the Sun's behavior within the broader population of magnetically active stars throughout the galaxy. The Sun continues its magnetic breathing today, much as it has for billions of years, winding and unwinding its magnetic field according to the same fundamental processes that operated when Earth was young and life was just beginning to experiment with complex chemistry in protected tidal pools, creating the rhythm of space weather that regulates the electromagnetic environment throughout the solar system and demonstrates the profound connections between stellar physics and planetary habitability across cosmic time. Magnetosphere's flexible boundaries stretch and compress like the surface of a living cell responding to changes in its environment, expanding outward during quiet solar conditions when low-density solar wind exerts minimal pressure, then contracting dramatically during magnetic storms when dense, high-velocity plasma clouds compress Earth's magnetic field to half its normal size. This invisible boundary, marking the transition between Earth's magnetic domain and the Sun's magnetic influence, exhibits a dynamic flexibility that allows it to absorb enormous variations in solar wind pressure while maintaining its essential protective function, breathing in and out with the rhythm of space weather like a planetary lung, exchanging energy instead of gases. The magnetopause, that invisible surface where Earth's magnetic field balances against solar wind pressure, maintains its position through a delicate equilibrium between competing forces that operate according to the fundamental principles of magnetohydrodynamics. On one side, Earth's magnetic field creates an outward pressure that attempts to expand the magnetosphere into surrounding space. On the other side, the solar wind exerts an inward pressure that compresses the magnetic field toward Earth's surface. Where these pressures balance, the magnetopause forms a flexible boundary that can shift position by tens of thousands of kilometers in response to changes in either the magnetic field strength or solar wind conditions. During quiet periods, when solar wind density drops to perhaps 3 particles per cubic centimeter and velocity remains near 300 kilometers per second, the magnetopause extends to roughly 70,000 kilometers from Earth's center on the day side, about 11 Earth radii, or nearly 1/6 the distance to the Moon. At this expanded configuration, the magnetosphere provides maximum protection against cosmic radiation, deflecting charged particles across a vast volume of space and creating the largest possible shield between Earth's atmosphere and the hostile radiation environment of interplanetary space. But when coronal mass ejections arrive, carrying particle densities 10 times normal values and velocities exceeding 1,000 kilometers per second, the dramatically enhanced solar wind pressure compresses the magnetopause inward to perhaps 40,000 kilometers from Earth's center, still outside the orbit of geostationary satellites, but compressed to barely half the quiet time distance. During the most extreme magnetic storms, the magnetopause has been observed to compress to within 25,000 kilometers of Earth's surface, bringing the boundary between terrestrial and solar magnetic domains closer to Earth than many artificial satellites orbit. This compression occurs not through gradual deflation, like air slowly leaking from a balloon, but through sudden jolts as pressure pulses in the solar wind strike the magnetopause and drive it inward in matter of minutes. Satellites monitoring the magnetopause position during major storms record boundary crossings that occur with startling rapidity, instruments detecting terrestrial magnetic field conditions one moment and solar wind conditions the next, as the boundary sweeps past their orbital positions faster than hurricanes move across Earth's surface. The magnetotail, that elongated extension of Earth's magnetosphere that stretches downwind from the planet like the wake behind a ship, exhibits even more dramatic flexibility than the day-side magnetopause. During quiet conditions, the magnetotail extends beyond the Moon's orbit, reaching distances exceeding 400,000 kilometers and creating a magnetic wake that influences the space environment throughout much of the Earth-Moon system. Spacecraft traveling to the Moon sometimes encounter this magnetic tail, detecting particles and fields that originated near Earth despite being located hundreds of thousands of kilometers away. During magnetic storms, the magnetotail undergoes explosive restructuring through processes called magnetotail substorms. Sudden releases of stored magnetic energy that accelerate particles to enormous velocities and drive them toward Earth's polar regions, where they create the brilliant aurora displays associated with severe space weather events. These substorms occur when magnetic field lines in the tail become so stretched and twisted by solar wind pressure that they spontaneously reconnect, snapping back toward Earth like rubber bands released from extreme tension and launching particle clouds earthward at speeds exceeding 1,000 kilometers per second. The flexible magnetospheric boundaries also exhibit wave-like motions called Kelvin-Helmholtz instabilities that develop when high-velocity solar wind flows past the slower-moving magnetospheric plasma, creating conditions similar to those that generate waves on the ocean's surface when wind blows across water. These magnetic waves propagate along the magnetopause with wavelengths measured in thousands of kilometers, creating undulations in the boundary that mix solar wind plasma with magnetospheric plasma and contribute to the complex particle transport processes that operate throughout the magnetosphere. The boundary regions themselves, transition zones perhaps 1,000 kilometers thick, where Earth's magnetic field gradually gives way to solar wind. Magnetic field contains some of the most turbulent plasma conditions found anywhere in the solar system. Here, competing magnetic fields create current sheets where opposing field lines approach each other and occasionally undergo explosive reconnection events that release energy densities exceeding those found in laboratory fusion experiments. Only took magnetospheric physicists until the 1960s to realize that these boundary regions contain more energy per unit volume than the cores of stars. Magnetic reconnection at the magnetopores operates continuously during periods when the solar wind magnetic field points southward, anti-parallel to Earth's northward pointing magnetic field in the region where they meet. Under these conditions, field lines from Earth and the Sun can merge and reconnect, allowing solar wind plasma to penetrate into the magnetosphere and energizing particles that will eventually create aurora displays in Earth's polar regions. The reconnection rate depends critically on the angle between the interplanetary and terrestrial magnetic fields, with maximum energy transfer occurring when they point in exactly opposite directions. The magnetosphere's flexible response to changing solar wind conditions involves multiple physical processes operating simultaneously across vastly different spatial and temporal scales. Magnetohydrodynamic waves propagate through the magnetospheric plasma at speeds determined by local magnetic field, strength, and plasma density, carrying information about boundary conditions from the magnetopores to the inner magnetosphere in time frames ranging from minutes to hours. These waves trigger particle precipitation, magnetic field reconfigurations, and electric field changes that affect the entire magnetospheric system. During the most severe magnetic storms, the normally well-organized structure of the magnetosphere becomes chaotic and unpredictable, with magnetic field lines tangled into configurations so complex that they defy simple mathematical description. The orderly division between open field lines that connect to interplanetary space and closed field lines that remain entirely within the magnetosphere breaks down, creating regions where field line topology changes rapidly and unpredictably as magnetic reconnection events occur throughout the magnetospheric volume. The plasma populations trapped within the magnetosphere particles that bounce back and forth between magnetic mirror points in the northern and southern hemispheres respond to magnetospheric compression by becoming more energetic as their magnetic confinement tightens. This adiabatic heating effect concentrates particle energy into smaller volumes, creating radiation belt enhancements that can persist for weeks or months after major storms, demonstrating the magnetosphere's ability to store and gradually release the energy imparted by solar wind disturbances. Ground-based measurements of Earth's magnetic field reveal the magnetosphere's flexibility through variations in field strength and direction that correlate with solar wind conditions and magnetospheric dynamics occurring hundreds of thousands of kilometers above. These surface magnetic variations, measured continuously at observatories around the world, provide a global monitoring system that tracks magnetospheric response to changing space weather conditions and allows scientists to study processes occurring in regions of space that remain largely inaccessible to direct measurement. The magnetosphere's flexible boundaries continue adapting to solar wind variations today, much as they have throughout Earth's history, demonstrating the remarkable ability of magnetohydrodynamic systems to maintain their essential functions while accommodating enormous changes in external conditions, protecting Earth's atmosphere and biosphere through a combination of rigid magnetic structure and fluid adaptability that exemplifies the elegant solutions that emerge from the fundamental laws governing plasma physics in space. Deep Time's magnetic memory lies frozen in crystals of magnetite and hematite scattered through ancient rocks, like tiny compass needles that recorded Earth's magnetic field direction and intensity at the moment of their formation, preserving evidence of this planetary conversation between Sun and Earth in mineral archives that span billions of years. These microscopic magnetic recorders, each one smaller than the period at the end of this sentence, contain information about magnetic storms that raged when Earth was young, about field reversals that occurred before complex life evolved, about the strength and geometry of magnetic protection during crucial periods in the planet's environmental history. The process of magnetic recording begins when iron-bearing minerals crystallize from molten rock, whether in volcanic eruptions that paint the seafloor with fresh basalt or in slowly cooling plutons deep within the continental crust. As the temperature drops below the Curie point, roughly 580 degrees Celsius. For magnetite, the mineral's magnetic domains align themselves with Earth's ambient magnetic field, creating a permanent magnetization that will persist for billions of years unless disturbed by subsequent heating, chemical alteration, or extreme mechanical stress. Only took geophysicists until the 1920s to realize that rocks could serve as magnetic tape recorders, preserving ancient field directions with remarkable fidelity. Each volcanic eruption creates a snapshot of magnetic field conditions at a specific moment in Earth's history, recording not only the field direction, but also its relative intensity through the strength of magnetization acquired during cooling. Successive lava flows stack these magnetic records like pages in a book, building chronological sequences of paleomagnetic data that document how Earth's magnetic field has varied over geological timescales. The most complete records come from oceanic crust, where volcanic activity occurs almost continuously along mid-ocean ridges, creating magnetic stripes that preserve millions of years of geomagnetic history in patterns that stretch across entire ocean basins. The oceanic magnetic stripes, discovered during the 1960s when sensitive magnetometers towed behind research ships revealed alternating bands of normal and reversed magnetic polarity parallel to mid-ocean ridges, provided crucial evidence for seafloor spreading and plate tectonic theory. These stripes record the history of magnetic reversals as new oceanic crust forms at spreading centers and gradually moves away from the ridge axis, carrying with it the magnetic signature of Earth's field at the time of formation. The symmetric pattern of magnetic stripes on either side of mid-ocean ridges demonstrates that oceanic crust forms continuously and spreads laterally, while the alternating normal and reversed polarities document the irregular timing of magnetic field reversals over the past 200 million years. Paleomagnetic studies of continental rocks extend the magnetic field record much further back in Earth's history, though with less temporal resolution than oceanic records due to the episodic nature of continental volcanism and the complex geological processes that can alter or destroy magnetic signals in ancient rocks. Some of the oldest reliable paleomagnetic records come from rocks formed during the Archean Eon, more than 5 billion years ago, when Earth's atmosphere contained virtually no oxygen and life consisted entirely of simple, single-celled organisms. These ancient magnetic records suggest that Earth's magnetic field was weaker than today, but still strong enough to provide significant protection against cosmic radiation. The study of paleointensity. The ancient strength of Earth's magnetic field requires more sophisticated techniques than simple directional measurements, involving laboratory experiments that attempt to reproduce the conditions under which rocks acquired their original magnetization. Researchers heat rock samples in controlled magnetic fields and measure how their magnetization changes, using this information to estimate the strength of the ambient magnetic field when the rock first cooled. These paleointensity studies reveal that Earth's magnetic field has varied dramatically throughout geological history, sometimes strengthening to twice its current intensity and sometimes weakening to fractions of its present value. During some periods of Earth's history, the magnetic field appears to have nearly disappeared entirely, creating intervals called magnetic quiet zones, where paleomagnetic records show evidence of extremely weak or chaotic magnetic fields. The most famous of these quiet periods occurred during the late Precambrian era, roughly 600 to 800 million years ago, around the time when complex multicellular life was beginning to evolve. Some researchers have suggested that this period of magnetic field weakness may have contributed to evolutionary pressures that drove the development of more complex life forms. Though the connections between magnetic field strength and biological evolution remain speculative. The magnetic memory preserved in rocks also records the wandering paths of magnetic poles over geological time, revealing that pole positions have varied dramatically as convection patterns in Earth's outer core have evolved. Virtual geomagnetic poles calculated from paleomagnetic data from different time periods trace complex paths across Earth's surface, sometimes clustering near the geographic poles during periods of stable dipole field configuration, sometimes scattering widely across the globe during periods of magnetic instability or reversal. Apparent polar wander paths constructed from paleomagnetic data provide powerful tools for reconstructing the positions of continents throughout geological history. As rocks on different continents record different magnetic field directions when the continents occupy different positions relative to the magnetic poles, the convergence of apparent polar wander paths from different continents provides evidence for past continental configurations and helps constrain models of plate tectonic motion over hundreds of millions of years. Only took paleomagnetists about 40 years to realize that rocks remember not only magnetic fields, but also the ancient positions of continents. The most detailed magnetic memories come from sedimentary rocks, where iron-bearing minerals align with Earth's magnetic field as they settle from suspension in ancient lakes and oceans. These sedimentary paleomagnetic records often provide higher temporal resolution than volcanic records, sometimes documenting magnetic field variations on timescales of centuries or millennia, rather than the longer intervals typically resolved by volcanic paleomagnetic studies. Deep-sea sediment cores contain particularly valuable records because they accumulate continuously over millions of years in relatively stable environments. Magnetic minerals in sedimentary rocks also preserve evidence of ancient magnetic storms through variations in magnetic intensity and inclination that may reflect periods of enhanced geomagnetic activity during magnetic storms. The increased particle bombardment of Earth's upper atmosphere creates enhanced production of cosmogenic isotopes that eventually settle into sedimentary environments, potentially providing correlations between paleomagnetic records and evidence of ancient space weather events. The study of magnetic reversals recorded in geological sections reveals that the reversal process typically unfolds over periods of several thousand years, during which the magnetic field weakens, develops complex multipolar configurations, and eventually reorganizes with opposite polarity. Some reversal records show evidence of multiple attempts at polarity change, with the field briefly adopting reversed polarity before returning to its original configuration, creating complex transitional behaviors that challenge simple models of geodynamo processes. Modern paleomagnetic laboratories use increasingly sophisticated techniques to extract magnetic signals from ancient rocks, while minimizing contamination from more recent magnetic overprints. Progressive demagnetization using alternating magnetic fields or thermal treatment can isolate different components of rock magnetization, separating ancient primary signals from more recent secondary magnetizations acquired during subsequent geological events. These techniques have revolutionized paleomagnetic research by allowing scientists to recover magnetic signals from rocks that were previously considered unsuitable for paleomagnetic analysis. The magnetic memory preserved in Earth's geological record continues accumulating today as new volcanic eruptions and sedimentary deposits record current magnetic field conditions for future paleomagnetic studies. In this sense, every volcanic eruption and every layer of sediment adds another page to the magnetic memory bank that documents Earth's magnetic field behavior, creating an ever-growing archive of planetary magnetic history that extends from the earliest Archean rocks to the present day and will continue growing as long as Earth maintains its magnetic field and geological activity. The quiet reconnection